As cloud service getting more and more popular these years, cloud storage is widely used by both individual users and enterprise ones. This leads to growing concern about information privacy. Users may be concerned about private information being stolen by service provider. And even if the providers are trusted, what if the servers are under hackers' control? Thus, a straightforward idea is to encrypt their data before uploading them. But it is not good news for the cloud service providers because according to the requirement of current encryption scheme, no information leakage of the plaintext is allowed. It means data deduplication is disabled even if the plaintexts are all the same. So to enable data deduplication and safe storage, a mission for them is to propose an encryption scheme that allows plaintext equality judgment and try to make it as secure as possible to convince the users to use it. Convergent encryption is one proposed method to solve the above problem. Its principle is quite straightforward. If we want the ciphertext to be the same, we can use the same key. And of course, a fixed key is not reasonable, so we derive the key from the plaintext. And so the encrypted one will also be the same if the plaintexts are the same, because their keys are also the same. And you can see here, we also calculate the digest of the ciphertext, the uploaded text, and we call it tag. It is a tool to help judge whether the uploaded data is the same. It also makes client-side deduplication possible, but it also causes some vulnerabilities. One is duplicate faking attacks, since if a bad guy upload a message whose tag is the same as the normal user, but the real contents are different, then the later and honestly uploaded one will be discarded, and the users will lose its tags. Okay, then I will discuss my solution later. And now there is still a question remains. How secure is the convergent encryption scheme? First consideration is IND-CPA. IND-CPA is widely accepted standard to measure how secure an encryption scheme is. Briefly, IND means indistinguishability, and CDA means chosen plaintext attack. So it means indistinguishability under chosen plaintext attack. And I would like to briefly illustrate it using the following graph. Given two messages M0 and M1 that is known by the adversary, he uploads these two messages to a challenger, and the challenger randomly chooses one of them to be encrypted, and then the challenger returns the encrypted one to the adversary and let him guess it is encrypted by which one. If the correct rate of the adversary minus 1/2 can always be ignored, then the encryption scheme is considered as IND-CPA secure. But it is obvious that CE do not have IND-CPA secure because whenever the adversary gets a plaintext, he will also get a key. Then a notion called PRV $CDA secure is proposed. Basically, it means a ciphertext of a known distribution data cannot be distinguished from a random generated string with the same length. And it can also be briefly illustrated with this graph in a similar way. Say, now the adversary do not have the exact plaintext, but he knows a distribution. And then the challenger generate a message with that distribution, then he encrypted it. And then the challenger also generate a random string that has the same names as the encrypted data. And he randomly return one of them to the adversary and let him guess whether it is the encrypted data. Okay, now if the successful rate of the adversary is again can be ignored after minus 1/2, then the encryption scheme can be considered as PRV $CDA secure. And convergent encryption has been proved to be PRV $CDA secure when the plaintext is random enough. It means its mean entropy is high enough. Now let me talk about my implementation. I have implemented a microfile system using convergent encryption in this term. The purpose of implementing this prototype is to measure the performance of some improvement design in my future works. This implementation uses SHA-256 as digest algorithm, and it will generate a 64-byte length hex string. I will have to convert every 2 hex number into 1 ASCII character. It uses AES-256 as encryption algorithm. The key it uses happens to have the same length as the previous digest. While adding a file, I will first calculate the tag to detect collision. If no collision happens, I just update the ownership and then store the file. Else, I will just update the ownership and discard the whole file. Okay, and every user has an independent directory. And while retrieving, I will use some auxiliary files to find the origin data and also to verify the ownership. And if the ownership is right, I will return it to the user. While talking about privacy, it is because it uses convergent encryption, and it has already been proved that it has PRV $CDA secure. And now there is a notion called tag consistency. Tag consistency is a tool to measure the strength under duplicate faking attacks that I've mentioned before. It has been proved that this scheme has strong tag consistency, but it is still not reliable enough because compared to the message, the digest is too short to be the only way for equality judgment. And I've proposed a design to make it more reliable. I introduced a database management system to maintain some relation information such as ownership, and basically it has 2 improvements compared to the former one. One is that the ownership information is protected even if the file system is under hacker's control. Another is that it is much more reliable because the digest comparison is not the only way to judge equality. For a piece of data, its digest is calculated and used as a file name. The file stores the content of the data. The attribute name is used to identify an uploaded file by appending UID with file name. And when collision happens, it will first compare the content of tag files and current data. If equality ensured, it will directly update the table, and if not, it will change the tag according to specific rules until the equality is ensured or no collision is found. So there is no need to worry about duplicate faking attacks or an unfortunate tag collision. And so when collision happens, it compares the whole content. It will not reduce user experience because all related works are done at server side. And there is no dramatic I/O increase because the false collision rate of SHA-256 is really low. And there still remains something to be discussed. For example, block-level deduplication can dramatically increase storage saving performance, but it requires block-level convergent encryption, which will reduce randomness, increase key size, and make the tag maintenance much more complicated. And for example, Client-side deduplication will dramatically improve the file uploading performance, but it again raises a false tag collision problem. And this itself will lead to duplicate faking attacks. And together with client-side deduplication, it will lead to hash-only attacks and some other side channel attacks. And for the above topics, I will find a deal in my future work.